Welcome to clickmyproject.com. We are going to see the product for memory reduced turbo decoding architecture using NII metric compression. Next we are going to see the abstract for our product. In our product we have implemented NII metric compression. The turbo code is one of the most attractive forward error correction codes which can provide near optimal bit error rates of Shannon's limit. Due to the fascinating error correcting performance, the turbo codes have been applied to various wireless communication systems. For achieving a high decoding throughput, an aggressive puncturing on long turbo codes is normally defined at the recent wireless standards. The extreme case of 3GPP LTE advanced specification, for example, necessitates a code length of 6144 bits and a code rate of 0.95. To minimize the performance loss in decoding of high-rate code words, the next iteration initialization scheme is widely accepted for the initialization of backward recursions instead of the traditional dummy calculation methods. However, the conventional NII technique requires additional memories for storing all of the final backward states of the current iteration, which denote the starting confidence levels of the following iteration. If the sliding window technique is used for practical realization, moreover, the number of NII metrics to be stored increases statistically according to the number of window boundaries. To mitigate the memory overheads, the static compression scheme introduces a dedicated transfer function to encode NII metrics into 3 or 4 bits. Most recent searches presents a dynamic scaling factor for encoding of NII metrics. The previous schemes still require a large amount of storage bits, as all of the state metrics have to be collected after an individual compressing process. To reduce the number of storage bits for our product presents algorithm for encoding and decoding of NII metrics. Next we are going to see the flow diagram for our product. In our product we have implemented NII metric compression for the turbo decoders. The architecture we have given address and the data. The address is 8 bits and the data is also 8 bits, which is stored in the RAM. Then the RAM outputs the 8-bit data with the 8-bit address. It is given as input to the interleaver. Then the output from the interleaver is given as input to the trellis state. Then the output of the trellis state consists of 8 bits is given as input to the NII metric compression. The NII metric compression has 3 architectures: max, min, max and min. The max min architecture uses one comparator and 2 multiplexers. The max and min uses one comparator and 1 multiplexers. The output from the NII metric compression is given as the compressed data. The proposed algorithm generates much compact information related to the minimum and maximum values among state metrics. In addition, the novel recovery scheme minimizes the performance degradation caused by the proposed aggressive compression with negligible hardware costs. The proposed NII metric compression also requires additional computations for the encoding and decoding processes. The computational complexity overheads. It is important to reduce the number of comparisons, which are much more time consuming than the encoding networks. The proposed compression technique dealing with 8 backward states denoted as beta WX. The number of comparisons can be greatly reduced by sharing the intermediate results. To find efficiently, 3 basic modules are utilized in the proposed architecture, that is already mentioned: max, min, max and min. The subbar clip unit computes the final output del x with a reduced bit width d dash. It's known that Imax and Imin can be easily generated by collecting the prior comparison results. Finally, we are going to see the output for our product. We use the software Xilinx version 14.2. To create the new project, click on File and then click the new project. That specifies the folder to which we have to save our project. Then click on the project new source to create the program file. Then add to our project. Here, to simulate the coding, we have to click on Simulation, Main, and then Simulate Behavioral Model. The simulation results will be shown in the iSim software. The NA metric compression technique we have implemented reduces the bit error rates. The iSim will be opened. Here specify the input bits. For AA, the input bits should be 8 bits. Then for BB, we give the right click the icon, then give the force constant, then enter the values 0 0 1 0 1 0 1 0. Then for the clock, give the clock pulse. Here we have to give the force clock. Leading edge value is 0, trailing edge value is 1, then period is 1000 nanoseconds. The enable is 1. Then for the D input, we have to give the value as 8 bits 0 0 1 0 1 0 1 0. Here the selection is 0 1. Then click on the run. The output will be created. Minimize the iSim. Here we have to give the turbo decoder data as given to the NA metric compression input. The output of the turbo decoder is given as input to the NA metric compression technique, that is beta W. Here mention the 0th bit as 0. Give the value according to that. Minimize the iSim. Then for the implementation results, click on implementation and click on the implementation design. Double click the implement design or right click and click on run. The implementation result will be running. The implementation result is created. To view the synthesis report, click on synthesis report and then advanced HCL synthesis report. Here we can see the number of flip-flops LUTs used for our product. The number of slices is 12, number of 4 input LUTs 23, and RAMs is 16. Then for the timing report, click on the timing report and timing summary. Here the delay time will be shown. The delay time will be shown here, data per delay time. For the RTL schematic, click on view RTL schematic, OK, and then add and then create schematic. Here the schematic will be created. Double click. The technological diagram will be shown. Thank you.